Today we have Simonas Grubinskas, who is a PhD student in Utrecht. He is halfway through, as I understand. And many of you know him because he also was a master's student here with the but now he's and also bachelor student there. But now he's an expert in applying field theory methods to solid state physics, and he's going to talk about one of the applications for instance. Please go ahead.
Hi everybody, how are you? So yeah, this is not my PhD thesis. My PhD thesis is some complicated stuff, that's whatever. But this is a couple of months project, 3-4 months project. It's somewhat reasonably easy, understandable, and actually fun. And it has some newness, some new angles to it, because quantum oscillation is a topic that is like 70 years old or something. But this is this has been noticed 2 years ago. So yeah, this is my supervisor Lars Fritz, and I belong to Leiden University and Utrecht University. So to begin, here's some experimental graphs from Ashcroft. And quantum oscillations is a phenomenon when values of some physical observables oscillate with varying external magnetic field. So to have that, you need to have very low temperatures, like 1 Kelvin, 2 Kelvin, and very high magnetic fields. Both are required because of the numbers. It's nothing special. It's just like some ratios of some quantities need to be 1. And by a large magnetic field, it's 1 Tesla, 2 Tesla, so on. Quantities that do display this oscillatory behavior are basically all other quantities. So let's say it can be magnetization of the material, it can be susceptibility of how temperature changes when you change magnetic field of the sound. It can be attenuation of sound waves. Even that changes or oscillates as you change the external magnetic field. And what you can notice here is, for example, at first for here high magnetic field, the behavior is somewhat chaotic. It's periodic but very disturbed. And then later on, for smaller magnetic fields, when you can still see some amplitude going on, they become more like sinuses and cosinuses, or maybe superposition of those. You see high harmonics, and then it's sort of like beating pattern. So that we remember. And since you see those properties in almost all observable, calculation of grand potential and seeing how grand potential oscillates with external magnetic fields should be basically enough to prove how this phenomenon arises. But now intuitively we have the following picture. Let's say we have a system that is subject to magnetic field. Energy levels are then quantized, discrete, and they're called Landau levels. And for example, for a simple 3-electron spectrum, the energy levels are spaced linearly, spaced at the same state all the time, and the energy is given by some energy scale that is proportional to magnetic field. So here, dimensions that are a bit off, so I omit them. And to Landau level number n, 1, 2, 3, 5, 6. And to quantum oscillations, high Landau levels, Landau level numbers are important, something like 100, 1000. So now I'm varying magnetic field. I'm lowering magnetic field here for magnetic field 6 and random numbers, not random units. It's lower to 5.5, 5, 4.5. Actually, it's exaggerated. It's something like very low variation in magnetic field. So the energy level here of the system, the specific chemical potential mu, when all levels below mu are occupied, behave like accordion basically. So as I lower magnetic field, the spacing between Landau levels gets smaller, and for example, this next unoccupied level above that level C gets lower and lower. This is below that, so you see here, gets occupied, and then keeps going lower, right? So it goes like that. So one by one, these levels, Landau levels, fall into the sea as you lower the magnetic field. And you can notice that the configuration of the Landau levels and the rotation numbers are the same for a magnetic field like 6 and the same as magnetic field 4.5. So if you measure external property that depends, for example, strongly on the density of states near the Fermi surface, so that only like the closest level to the Fermi surface is important and gives contribution, then you will see a periodic, well, in this case, nicely plotted behavior in external properties such as oxidation, thermal capacity, and whatever. Yeah, so for a long time it seemed that a well-defined Fermi surface is required, because how are you going to get that behavior if you have no Fermi surface? Meaning that these Landau levels cross Fermi surface. So if there's nothing to cross, there won't be any oscillatory behavior. But in reality, when you look at it mathematically, you don't need really the crossing of the Fermi surface. All you need is that the level would be in a motion that is towards the Fermi surface and then away from it. So at first it goes to the level goes towards the Fermi surface and then away from it. Also, contribution to physical variables from the excited electrons and excited holes is the same. So the system is kind of symmetric. So just because it is occupied here doesn't mean that it's very important. So it's as if the let's say distance from the chemical potential from above and from below, these two levels are the same, they contribute the same amount to any thermodynamic property. So we have that. Next. Chemical potential cannot be too small. For example, it cannot lie here if this is the first Landau level. This is first Landau level and chemical potential is below it. If you, let's say, increase magnetic field but decrease it, all the Landau levels will stay above the chemical potential and not really do anything. So they can go towards the chemical potential, but cannot go away from it and make a reasonable oscillation. So now,
can I ask a question? So does it mean that it only happens in metals, for example, where you have many free electrons?
Where chemical potential is big, where below the Fermi surface there's thousands of Landau levels, and then metallic states only. So no semiconductors and no insulators. So for insulators, you're not going to have any quantum oscillations, but for semiconductors you might. So that's the whole point of quote-unquote anomalous quantum oscillations, is that you have some oscillations in systems that are semi-metals or semiconductors, or you should have. So now I would like to construct some sort of model for that, right? So if you just, like how I imagine the system is in this way. So it's like, again, one-dimensional system or whatever, that's described as one quantum number. These levels are here and then go up. And as a very magnetic field, these Landau levels come from the plus infinity downstairs, make a turn, and go to infinity. So now, again, if the temperature is sufficiently low, this motion of the most nearby electron level is most important, and it goes to the chemical potential and then away from the chemical potential, thus making some sort of periodic contribution. I modeled it on mathematically, it gives you nice oscillations, whatever. It gives you a bit jagged oscillations because it cuts the cosinus in half, because there's only one band here. Okay, never mind, it would still work.
Can I? You draw this picture so then E is energy.
E is like energy, like spectrum.
And what is on the horizontal axis?
On the horizontal axis, there's nothing. It's like it would overlap, right?
Yeah,
so on the previous.
You plot the graph, so it has X and Y axis.
No, so basically, if I put it back together like that, like it should be, you wouldn't be able to see how it moves. So it's like they're both vertical. So one band goes up, not band, but one part of it goes down, another goes up.
So what's the meaning of the distribution of the points?
Meaning of a distribution of more points, yeah, absolutely. So basically, here it would mean that exactly the same plot as here. What's the meaning of that distribution? What's the meaning of the distribution here?
You tell
You tell me.
I don't see any meaning.
Yeah. So okay. So there's so this is just one line energy, right? And these points are separate Landau levels.
Yeah, I understand the one level, one level, but on the next picture,
So they're still the
you
same.
want a parabola.
They're still the same.
Why?
No, I'm telling you, they're still the same. On that particular picture, still the same. So it's basically one-dimensional level of one-dimensional picture where, let's say, here is 47th Landau level, right? And then it goes down and up, and then it's 46 comes up, and so on and so on.
Yeah, but now levels are Vn.
So here you number levels somehow. In previous picture you could also number levels and it would be like a linear.
Yeah. So basically, if you want, I could draw a little arrow here and right hand, and then previous picture would be 45 degrees or something.
But I think since you have parabola, probably you just plot on the.
I didn't say we have a parabola. That's the whole point. Like, forget. Pointing in this picture, I begin with just a picture, and I want to reproduce this picture with formulas. And I'll tell you that it's not so easy.
What is the meaning of the dynamics state? It goes down and then up.
As you change the magnetic field, the spacing between Landau levels changes.
Yeah.
So imagine the first Landau level is always on the floor, and then second, third, fourth, and now fixed chemical potential here. Tell me what 15th Landau level does as I change the spacing between Landau levels. It goes up or down. So this is that going up or down. And then it gets occupied or not occupied, and then if it is near the thermal surface, then it's important, it gives contributions to observables. So that's the point. And now I'm trying to construct a system where this variation comes out without crossing thermal surface. So now, I would like to try the following spectrum. It's an arbitrary spectrum. E squared over 2m kinetic energy squared minus some constant times kinetic energy. So now I would have this quantization, so Bn squared minus Cbn. Now as a function of n, actually, or let's say as a function of n, here I would have quantized levels, and my quantized levels would be a parabola that has a minimum here, and I would expect maybe that these Landau levels coming down and then up again would give me these quantum oscillations that I want. Problem is that for any normal function, calculus tells us that at minimum the slope is 0. So previously the condition was that the temperature should be much smaller or somewhat smaller than the spacing between Landau levels, because you only want to see one Landau level that is important at any given moment. If you see 10 of them, then the difference between seeing 9 and 10 is exponentially spread, that there's nothing going on. Same thing applies here. So the point is that although you might have a pretty normal spacing between Landau levels up here, right? As they go down and reach the minimum of a parabola, there's basically nothing left.
I'm so confused. Okay. Typically, let's say you choose a Hamiltonian on spectrum, and then you field minus spectrum again, and then try to make a matching between the two. Now, you get an answer of the spectrum, and then you assume that if you add magnetic field, you will still be able to get an answer from the previous answer.
Like this arrow, no? Not like.
I don't understand what you are doing here.
Well, if you put a spectrum, put a spectrum with that equation, and you see there is magnetic field in that equation, and you change this magnetic field is that for you.
So without the magnetic field, you already know the spectrum, and you assume that you also know a spectrum with magnetic field.
You solve it.
Just solve this magnetic field.
Step number 1.
When you write down the Hamiltonian, does it correspond to any real Hamiltonian?
No. It's speculative at this point. Like 2.
So you get the spectrum, but there is no Hamiltonian.
So it's a Hamiltonian.
There's the Simonas coupling. If you have Simonas coupling,
instead of n you have k square, and it would be like, if it was spin, of course there is no spin, but all like shifted oscillator, I would say. Not coupling is shifted oscillator, but the shift was spin up and spin down in opposite direction.
And you,
Yeah,
okay.
but the
It's just, yeah, it's one more power.
enters in the
Yeah.
fourth power. So
Yeah, so it's hard. It's basically fake.
let's assume we have this.
Yeah, so step number one, you get a spectrum. Step number two, you solve it for the Landau level, which basically amounts to substituting kinetic energy for V dot n. And then you see how the levels behave. Then you put it on Mathematica, see if you get anything. And for example, for this naive guess, let's say, where you have a minimum somewhere and there's some energy levels coming in, down, and up again, you will not get a reasonable result because this is too flat.
So do you assume that you say, okay, now you have some material and here some value or here some minimum, you can approximate your spectrum with that. You have some weird material or
Oh, it's going to be completely normal material, but yeah.
no, it's not this is good normal.
Because usually spectra when spectra quantize semi-classically, all you do is just take a normal spectrum and just dot it. It's like that. It's not complicated. Like,
Depends on the order.
Still confused what you mean when one type is dot.
quantize means subjected to magnetic field.
Is it really true? No matter what kind of engine the person has.
How we can vote?
magnetic field
Is it
just,
reasonable?
Well, of course, approximation.
I mean, you definitely need
You get a quantization level, right? That's a reasonable
Oh, because the
approximation.
K axis, okay.
And then you can take into account the different levels are shifted around, different people. Simonas is taking a model, and he's looking if he can get the effects he wants from the model.
No, but you need to remind people who have forgotten. So you quantize, okay, it's the K, you should quantize.
Yeah. I'm sorry, what did you say? K is not quantized magnetic field. It just happens that K is a good quantum number for a free system, and then later you have to come up with another quantum number. And that happens to be n, which is then which is more quantized than before. And by more quantized, they mean quantized by the properties of the magnitude of the magnetic field and not the length of the box as previously
So if
came.
I'm the only one who is confused, we can proceed. But I'm confused now. I'm the only one who's confused.
We'll have to, yeah.
You understand too much. You would understand less. You wouldn't be confused.
No, for consensus, for
Yeah, but still the spacing between energy levels.
This funnel is not equal. It's not equal.
Because if you fit this parabola, you can assume that you can number these levels by some kind of integer and get like a parabolic inversion. Yeah, but if you have parabola, you know.
I understand the point.
So now Simonas will show some examples.
Yeah. So now, again, so what does the job, sort of, is the following spectrum. So this is the following spectrum. It still has some quadraticity in it because it's p squared and n squared, but then it has a square root. Usually it's not, you can see it's not a one-band model. There's a square root going on. So you need a Hamiltonian that is something like 2 by 2, and then in 2 by 2 Hamiltonians you have discriminant, there's a square root, and then you have, and then you are able to have the sum.
So you have two dispersions, one with positive, not another with negative.
This is not needed. It's just like I already know what the answer is going to be, so I'm already putting that second branch down there. But in principle, this works with one upper branch.
Like electron volt and you couple them somehow.
Pretty much. I'll show you how this model is constructed. It's by Larry Garfin. After quantization, you again see the same trick, right? P square of 2m becomes omega c times n.
Now I return to the cyclotron frequency, which is a proper energy measure of the spacing between energy levels, Landau levels up here. It obviously changes when you go down here. Now this function is very important because if the gap delta here is 0, this function as a function of n is not differentiable at its minimum. So it has this little sharp turn, right? With a square root. It's basically a square root of x. Square root of x, of modulus of x, is a very sharp function. So it exactly reproduces what I wanted down here. It goes down here, basically bounces back off chemical potential, goes up again. Now, if I have some gap going on, which I want to have.
Also the persistence in that case.
Oh, absolutely.
Because you think about like the batic motion, but the persistence you have the sharp edges, it would not work. Because in the limit of zero gap, you have nothing. You have just two parabolas which do not talk to each other.
Yeah, you're inventing a new energy field, right? Like you're thinking about experiment, and now I'm tuning not tuning, but like changing the magnetic field at a certain rate. That rate must be smaller than the electron readjustment rate. And then you're saying, aha, there's an infinity down there, but it's just a formal, it's just formal basically. If you do things reasonably, electron readjustment rates are picoseconds. You're not going to change your hand to this picosecond speed, so no. Instead of picoseconds, you will need not more than microseconds. So what? So this is natural two-band model, and this is the configuration of Landau levels that we obtained. You put that into Mathematica, you get super awesome oscillations. They don't decay fast. They just decay as they're supposed to be. What next? Yeah. So I'm now telling you what this gap delta will do, or how it will mess up the experiment, and why it is, as I understand, still not a very well observed phenomenon. So that I take some semiconductor, I measure quantum oscillations, and I see them. So far I understand they don't see them. And this is so. This is why. But just one remark that previously for normal metal, for one-dimensional metal, one-dimensional spectrum, I should say, we have a spectrum omega c n, and that requires, because the spacing is omega c, that the spacing be bigger than the temperature. Okay, that's reasonable. Now we linearize our spectrum around the minimum of that spectrum we saw previously. And since there's some finite delta, it's a function that you can expand, and this is the energy spectrum that we obtain. And since only several Landau levels that are around this point are important, it's basically equivalent to the spectrum down here, up here. So what we see here now is that not only omega c must be bigger than temperature, but this renormalized constant can mess that inequality up. So what we require is that the whole prefactor here must be bigger than temperature. So for example, if the gap is of the order of omega c, it doesn't mess up anything, but if the gap happens to be several times the size of cyclotron frequency, then this inequality is broken, and then, sorry, you have to readjust your system. So now, you not only have to have big magnetic field, small temperature, you have a gap that is small, but also big enough so that you will detect it in the end. So this is the experimental challenge on mathematician, so it doesn't matter at this stage, basically. It's,
I'm still thinking, if you can discuss, okay, look, if you have a Hamiltonian and you have a spectrum, and then I saw what they got, that if you have some magnetic field, you don't have to solve anything new, you already know the spectrum.
well, it's let's say, let me make the,
Is it actually, so I actually am thinking, so when you have this two valves with stress tape, you can, in the previous picture, you just reshape your kinetic energy. Yes?
You go here or where?
And you are working in this minimum, and you have effective mass, and on the top you add Landau magnetic field, and you call this effective mass. You're solving or not exactly.
Yeah, that was the initial thinking of everybody, but to say effective mass is wrong. For the reason I will try to explain next slide.
So how you get the second equation from the first?
Second equation from that's interesting. Okay. So basically, yeah, good. So basically, so that's the model.
Okay.
So that's the model. So you have bilayer graphene, right? So where's this? You have bilayer graphene, this cone here, and actually bilayer. So there's two cones, well, 4 cones in total, right? So there's overlapping cones here. So basically a core energy band. Now you touch them, you make them hybridized, and they split off into 2 quadratic bands and 2 high energy bands. So you sort of get rid of those 2 quadratic high energy bands, and you're left with these 2 nice quadratic bands. What you do next, you apply bias. So basically I understand voltage across the 2 layers, so that one layer on-site energy gets smaller by, let's say, half a delta, and another gets bigger by half a delta. So those 2 parabolas get switched into each other, right? Get pushed into each other.
So you just make that each layer has different energy. Wouldn't it mix or just shift in that case, because this is actually...
And it mixes. And it mixes.
And
then here, at these points, of course, the Dirac cones won't live, or it will be kind of difficult for them to live. You might do that if you keep certain symmetries. So now we'll go to zero, that's okay. But in general case, absolutely, they hybridize, and here you open a gap. So then it's sort of 2-dimensional spectrum, like a hat potential, with gaps open here and here, and everywhere around that minimum, and then you get this spectrum.
Yes, but what is the operator?
The
operator.
What is the operator? Okay, so basically it's 2006 paper. It's paper by McCann in 2006 or 7. Basically, he obtained a low energy Hamiltonian of this bilayer graphene. That's basically this Hamiltonian, right? So let's see how it looks like. Where is the Hamiltonian, guys?
Actually, the question by Richard is very relevant, because if you ask what is operator, Simonas should write somewhere that there is no board, so we need to buy a board for this. So, but we need to ask Gintaras Valushis to allow to play. Probably we should play it maybe here. The speaker could come here and play, and after that.
Most of the questions get up from the back of the room.
So that's the Hamiltonian. So the delta you see here with the twiddle is the bias. The C squared is the 2 quadratic bands. See, this is quadratic band that is looking downward. This is quadratic band that is looking upward. And these are the mixing terms that appear. But then you have to go back to McCann's paper, and then his Hamiltonian is 4 by 4, and then he does some stuff, and then you obtain this Hamiltonian. So for a real Hamiltonian, you have to go back one step. So I'm not going back one step. So from this Hamiltonian, for example, yeah, okay, maybe it's not super intuitive, but basically, when you introduce magnetic field, these operators P means dx plus I Py, using the procedure that is in this paragraph, basically almost always become either A dagger A plus 1/2, A dagger A minus 1/2. If it's, P star times P star, then it's A dagger A dagger. If not, it's A. solving this Hamiltonian nicely, perfectly in a two-band system, in a how do you call it, Hermite functions, right? In exact basis of Hermite functions. Yeah, it's not so easy. I obtained some solution. It needs it's not like it's like a two spinor. It's like pi n minus 2. It's not that. It's more like two terms each time. So then instead of 2 by 2 equation, we have 4 by 4 equation. Doesn't matter. Why? Because we're talking about Landau levels that are of the order of 100. So if you act on n minus chi n minus 2 or chi n, this factor will produce approximately 100 squared or 100. So we can solve this, but when you take n to infinity limit, you will just get n here, and now you take this Hamiltonian, take that Hamiltonian, you can see how p squared became a dagger A, which is n times this little cyclotron frequency. And basically this quote-unquote how I take any even Hamiltonian and just replace it immediately. I did it once, I can do it for any other spectra that are in the following form, okay? My statement was maybe a bit too general, so if you have the following system, then you can sort of put it here. So we have that. We have it
Okay,
here.
that's much better, that if there is some way one can check.
Yeah. No, previously was that, so first few slides were quote-unquote intuition, you like it or not, whatever, but if you want a step-by-step approach, so first step in the logic is always to think about this hat potential and to think how Landau levels will slide past this minimum. And the reason why you cannot think about effective mass is if you have actual effective mass, then if you think about effective masses, then you will go back to this Hamiltonian, which is actually consisted out of masses. So if you try to take this Hamiltonian, expand it around the minimum here, think that the expanded Hamiltonian corresponds to some mass, and then use that mass in the cyclotron frequency, which is E d over m star, effective mass, you will get a wrong answer. Why will you get a wrong answer? Because it is not a parabolic system. It is a special class of systems that are that have been a cone of some sort, and cones don't have mass. And in this case, I can even draw you another system.
Yeah, but if it's not like graphene, if you open up like the cone, if you open it,
it gets a mass. Yes, absolutely, it gets a mass, which is at the zero momentum. It's a reasonable mass. Here is a mass not there.
No, not at zero, at this touch around in the vicinity of touching points.
Which are equivalent, which are kind of zero.
So here is also this vicinity. You have roughly approximately.
Oh, here absolutely. Here is a mass.
No.
And here is not a mass. Here is like a cone. It's a two-dimensional spectrum. It's a half potential.
Two-dimensional mass.
Well, it's graphene.
Yes, it's two-dimensional mass.
You see how I classify masses. Masses have to be useful. Like if I have a mass that has a property that I can put into a formula somewhere else, then it's qualified as mass. If you expand something up to second order and say that it's a mass, I say it's a misleading name for a mass because it's useless. You cannot use in all these other formulas where you could usually use dress mass, effective mass. Semiconductor is not a thing that doesn't have effective masses, but this is not effective mass. And actually there can be a lot of systems that you construct in a similar way. For example, I saw a paper that has exactly the same treatment. It's a parabolic band, that's it. Another band is a straight line. And you don't have anywhere to draw.
And basically, what happens is at the fetching point, that thing gets like avoided. And one of the bands is basically just flat. Sure. And one of the bands is basically flat. And the system picks up quantum oscillations on that weird fetching point. Although the bands are not like nice like here, like having a mass. Their mass is what? 0 or infinite if the band is flat. So it's not even expandable up to second order that energy is. Still, quantum oscillations are picked up by the fact that the system feels that it should, in principle, cross. That those energy levels should cross. So, for example, here, when there's no gap, energy levels go up here and down here. So there's 2 contributions to quantum oscillation. If I open a little gap here, this goes down and up, this goes down and up, which is basically completely indistinguishable from what I've said 5 seconds ago, right? This sort of imaginary branch is still going up, this imaginary branch is still going down. Now, I'm taking this Hamiltonian, this spectrum basically, I don't need Hamiltonians, this spectrum, and I'm calculating the omega, the grand partition function. So I'm calculating is it 1 hour and 15 minutes? Is it 45 minutes?
Well, 1 hour with questions.
Okay. So I'm calculating partition function. You get that probably there's more than one way to calculate a sum, right? And more than one way to approximate it. So this we like the best, and this is our method. And this is the only reason why there's some field theory in my work, because this is Green's function to the power of -1. It's undressed, it's a free system. This is the Green's function to the power of -1. And there's a logarithm going on here. And go ahead. So if you sum this Matsubara frequency, you will obtain the old normal classical statistical mechanics result of logarithm 1 plus exponent. But here you leave out this Matsubara frequency. What you do is Poisson trick. Poisson trick is awesome. Why? Because nobody understands. So you take this discrete sum over n and replace it by discrete sum over k over these cosinuses, oscillations. 2 pi k times x, where x is this n. You have this energy dependent on quantum levels, and now it depends on x. We just replace n by x. And this sum is from k1 to infinity. Discrete sum of cosinus, not over one Brillouin zone, but over all of integers. And there's also integral over dx. So I really want to share with you. So basically, if you take a cosinus like that, and sum over first Brillouin zone, so basically k from 1 to, I don't know, 1 over x maybe here, right? Then you will get a delta function that is centered at the center of the Brillouin zone. Now, if you sum over second Brillouin zone, you will get a delta function that is centered around the second Brillouin zone. So you have a delta function, many delta functions that are centered around 0, 2 pi, 4 pi, 6 pi, so on, right? 2 pi is of course factored out, so at 0, 1, 2, 3, 4. The sum of delta functions that are centered at integers. Delta of x plus delta of x minus 1 plus delta of x minus 2, so on. Now, boom, integral from 0 to infinity picks up all those contributions and you get back this sum over x. That's awesome. By the way, this should also be like this twiddle here, because there's another contribution that's just 3 or 4 contributions that I'm only looking at this sinus here. Next step, I extend the integration of x to minus infinity. Yeah, this is a step that is kind of subtle, so anyway.
Sorry, could you comment a little bit? What is M and N?
M is Matsubara frequency label, I omega M. Matsubara frequency is pi to n plus 1 t. Is when you, in field theory, you go to imaginary time, right? And all that. It's imaginary time.
Yeah, so
Absolutely, yeah.
Is it just a dummy number, or is it somehow related to the one? Is it always summed over this m, or could it be observed in the initial or final state?
If you remove this discussion from everything else, you can say that sometimes, well, not sometimes, but for example, response functions to current correlation function will, when you finish calculation, depend on I omega n. Yes, it will depend on I omega n. What will you do then is do the analytical continuation, quote unquote. I omega n will go to omega plus I epsilon, and then you will get real and imaginary parts of the response function, where that omega in the real axis will be, well, I don't know, the frequency of external field, electric field, that makes your system react to you. But if you rotate it on the imaginary axis, then it's temperature, quote unquote.
Okay. So is this related to a real quantity, just like rotated?
Yeah. So there's a whole discussion about what is Keldysh formalism, how you can either get time dependence or temperature dependence in field theory. You cannot have both. So this is imaginary time formalism, meaning that you only get temperature, and this formalism, in this particular problem, we only care about temperature dependence because, hey, I was talking about how if temperature is too big, the oscillations will die out, right? So I want to see how fast they die out. Now integration by parts. Easy. Cosinus becomes sinus, and this logarithm goes down. Now important step is the following. See this integral, right? So there's some x going on, right? And there's some simple pole in the denominator. By the way, I'm taking now 3 electron cases because I think it's fun. 3 electron cases because it's solvable. So now you're going to calculate a pole. Pole has a real part, chemical potential, and imaginary part, the temperature, sort of. So the real part, basically all of that as a pole will go into the sinus if you use calculus of relationship, right? So you will have sinus of mu, which gives you the oscillations. Proves that in this system will exhibit quantum oscillations. This one step rule. Then you see that I omega m will go also into sinus. Sinus of an imaginary number is decaying exponent. So it will be suppressed as an exponent. Then you do some math, you sum over Matsubara frequencies in the end, and you get a sinus of k mu, how it oscillates, with varying magnetic field, and here we see that the oscillation period is given actually by 1 over b, not b, 1 over b, what the experiments initially showed, and the damping function sinus h, essentially. So meaning that first kind of normal, and then it goes down exponentially.
What is the meaning of that duality? So you have dualities, 1, 2, 3, 4.
Yeah, it's not that similarity relation in yeah, but also approximate I don't like because approximate means like there's a little bit of an error. And here similarity, like I define the symbol to mean only oscillatory behavior survives. It's not, well, it's approximation, but it's extraction, it's physical step of extracting the information I want if I want to proceed.
Yeah, but can you repeat what is the meaning of that sign?
I just told you. So you can repeat. Can you repeat the sentence? So what did they say?
I don't understand what's the meaning of that similarity sign. Can you explain it?
Yeah, so I said a sentence. Can you repeat it?
Sorry?
I said an answer that contains a sentence. Can you repeat it? If you cannot, it means you don't remember. If you don't remember, it means you didn't listen. So, actually now I'm going to my actual spectrum that they have, right? My actual spectrum is this guy here. And now you have to close your, no, not close your eyes, but like look really careful what will happen here. Imagine the chemical potential is not here. Chemical potential is zero. It's between the, it's in the middle of the gas, right? So what will contribute to the oscillatory behavior here? So I need a pole that will have a real part, and this will give me cosine. Look here, temperature will not give you real contribution. If you look here, this delta squared will go to the left-hand side of the equation, so it will be minus delta squared. You will take square root here at some point. That will give you I, the imaginary number. So this is also a damping function. But here you see that in the very, very end, you will see this. So F will have some real part, which will be delta. And the delta was the position of the minimum. That minimum. Position means here. And this is how you, this is the proof that these oscillations will happen because of this minimum. Well, that's it. Okay. So this function has a this result has a damping function. Damping function behaves a complicated way. You cannot really write it down. So, again, so it's just a contour plot of a damping function. If you increase temperature, amplitude goes down. If you increase the gap, amplitude goes down. Exact relation is plotted here. Thank you.
Okay, any questions?
I have a question. Can you repeat the meaning of that?
Yeah. So, for example, as I say, it's like when you do this, it's equivalent relation. Yeah, but like.
Okay, but what do you mean by that sign?
Let me look. What exactly do I mean? Here.
I can understand equality.
Two things. One is integration by parts. So when you integrate by parts, you get some boundary terms. And boundary terms, in my case, do not have this cosine. I mean, like write something into that cosine. Aha, but there's a catch. Cosine of infinity, cosine of 0, what does it mean? So exactly, it's like, throw it away. Well, I mean, here, I extended to infinity, minus infinity. So there's two steps. Yeah, so there's two steps. First, you extend to minus infinity. That's 10-minute discussion. Boundary terms is...
Yeah, it can be an hour discussion, but what is the meaning? I mean, you have...
You neglect some terms.
So you just leave the terms which are converging.
For example. No. Yeah, that's even, yeah. So it's not rigorous at all. So it's like, as everything in quantum field theory.
The divergent integral and you just take only the convergent part.
Yes. Because divergent integral in practice has some regularization. It will give you answer 17, for example. Doesn't correspond to anything. You won't see it in experiment. If you want, it's an artifact. It's an artifact from the fact that you sum over the infinite amount of occupied Landau levels.
Simon, this is simpler. You know the answer, and you were learning the way how to obtain that answer, but some parts you will not do the confidence.
So I'm going through. I mean, yeah, I'm going forward.
Yeah, I think you know the answer, which can be obtained by some other ways, and you try to learn how to obtain that, but some parts will not get there, and this is the process.
Well, the process is finished because I will not make those other parts. But for example, if you ask my supervisor, he will say, "Oh, those other parts are containing Landau diamagnetism."
Yeah, so you get an answer which makes sense, and you try to model show how to get it.
Yeah, but that answer doesn't apply to it. It doesn't work. So that, like, you're repeating it because it was my first answer, but it's not. This is my basic best answer. What you just said.
Okay, more questions?
Well, I have one question. So, in the abstract of the talk, you promised to tell us about something that has no Fermi level. Was that implicit in the discussion?
Yeah, so I also asked Lars, like, wait, so chemical potential is 0, so that's where the Fermi level is, no? So he said, no, if it's unoccupied at 0 temperature, Fermi level is defined as something that electrons occupy at 0 temperature. And that mu equals 0 is not that. It's unoccupied. So there's no Fermi level.
Okay, so by no Fermi level, you mean that mu is equal to 0, like it's in the middle of the
gas.
Direct cone or the gas in the case. All right.
So in the middle of a, it's kind of logical because in the middle of a Dirac that point, the Fermi level is said to have 0 dimension. So it's even less than that, probably not.
All right. So if there are no further questions, let's thank the speakers again.